Hello and welcome to this video looking at acids and bases. We're going to look at the calculations involved with strong acids and bases and weak acids and bases. We will start by looking at the reactions between strong acids and bases. Here is a generic reaction for a strong acid reacting with a strong base. In reactions between acids and bases, our products can also be given new names. The species which is left over when the acid has lost its hydrogen is called the conjugate base. The species which is created by the base accepting a hydrogen is called a conjugate acid. The stronger your acid, then the weaker your conjugate base will be. Your conjugate base is usually this negatively charged species which could accept an H+. However, if your HA is an extremely strong acid, then this will not accept an H+ easily. The same applies to your base. The stronger your base, then the weaker your conjugate acid will be. Your conjugate acid will not want to lose the H+, and therefore this will be a weaker conjugate acid. Water is a special compound in that it can act as both an acid and a base. Here we have the auto-dissociation of water, where one water molecule is acting as an acid to lose an H+ and to form its conjugate base, OH-. Another water molecule is acting as a base and through its lone pairs is accepting a proton to form its conjugate acid, the hydronium ion. Protons are very small, and this means that they cannot exist by themselves. So this is what we find in an acid, an H3O+. To go from water to a hydronium ion involves a slight change of shape. Water, as you know, has this non-linear shape with two lone pairs on the top of the oxygen. The hydronium ion has a shape closer to that of ammonia, where it's pyramidal with one single lone pair here. As this is an equilibrium reaction, we are able to write an equilibrium constant for the reaction. So K will equal H3O plus multiplied by OH minus divided by H2O squared. If you watched the previous video, you'll know that H2O, as it's a liquid, gets a value of 1, which means we can simplify this to H3O plus multiplied by OH minus. In fact, to make it simpler still, we write KW, as this is a special case, and we purely write H plus multiplied by OH minus. You'll find that on the last page of your data book this is called the ionic product of water and has the value of 10 to the minus 14 at 24 degrees. These three equations can be found in the front of your data book, and these are to be used with strong acids and strong bases only. The clue is that strong acids and strong bases fully dissociate to produce H+ and OH- ions. Let's have a look at some example calculations. So the first one here is to calculate the pH of 0.2 moles per litre nitric acid. For this, we are going to use pH equals minus log concentration of H+. Nitric acid is a monoprotic acid, so the concentration of our H+ ions is the same as the concentration of our acid. So if you do minus log 0.2, you'll find that you have a pH of 0.7. Let's now look at calculating the pH of a strong base. There are two ways to do this. One way is to use the relationship 14 equals pH plus pOH. To calculate the pOH, you have minus log concentration of OH. The concentration of the OH- ions is the same as the concentration of the alkali. So if you have minus log 0.3, then that equals 0.5. You would then do 14 minus 0.5 to equal 13.5 as your pH. The second method uses our ionic product of water, Kw, and if we assume that our sodium hydroxide is at room temperature, 24 degrees, then we have 10 to the minus 14 equals the concentration of H plus multiplied by the concentration of OH minus. If you rearrange that, then you'll get your concentration of H plus, which will be 3.3 times 10 to the minus 14, and then you can put that into the pH equation. So negative log concentration of hydrogen ions, and if you put that into the calculator, then you'll get a pH of 13.5. So you get to the same answer using either method. Pause the video now and try these two examples yourself. This first example looks at calculating the pH of hydrochloric acid. So we only need to use one equation, pH equals log of H plus. Your H plus concentration is the same as the concentration of the acid, so it's log 0.5 equals 0.3 for your pH. The second example is trying to calculate the hydrogen ion concentration when you have a certain pH. So if you have pH equals minus log of H plus, you need to rearrange that for H plus. So the concentration of H plus will be 10 to the minus pH. So we'll have 10 to the minus 9.6, and if you calculate that through, you'll get 2.5 times 10 to the minus 10 moles per litre. If we look now at weak acid and base reactions, for any weak acid, it can dissociate in water into the hydronium ion and A minus. We can simplify that to just be H plus and A minus, and we can write an equilibrium constant, Ka, as it's for a weak acid, is H plus multiplied by A minus divided by HA. Notice that I am ignoring the H2O as it is a liquid and therefore has a value of 1, so can be ignored from the equilibrium constant. We can then do calculations using Ka. You can calculate a pKa. Whenever you see a small p, that is minus log 10 of whatever the value is, and you can then use this to calculate the pH of a weak acid. A weak acid does not completely dissociate into hydrogen ions, and therefore its pH depends on how much it has dissociated and the original concentration of the acid that you have. Values for Ka and pKa for common weak acids can be found on page 13 of the data book. However, you should be able to calculate Ka and pKa from values provided to you. This first example is asking us to calculate the pH of 0.2 moles per litre ethanoic acid. You need to be familiar with which acids are weak acids and which ones are strong acids so that you'll use the correct equation for pH. The equation that we need to use is pH equals a half pKa minus a half log C. You've been given C in the question, 0.2, and if you look up in the data book you'll be able to find the pKa for ethanoic acid. So the pKa for ethanoic acid is 4.76 minus a half log 0.2. If you work through all of those calculations, then you'll find that this has a pH of 2.73. Try these two examples yourself. Remember to use page 13 of the data book to get your pKa values. For this first example, using pH equals half pKa minus a half log C. The pKa for carbonic acid is 6.35, and the concentration that you've been given is 0.3. That gives you a pH of 3.44. For benzoic acid, you have a pKa value of 4.2 and you have a concentration of 0.47. And that calculates out to be 2.27 for your pH. When you're using the pH equations, you need to make sure you know which is used for which circumstance. The clue in this equation that you use it for a weak acid is that it has a Ka part here in the middle of the equation. You can only have a K if you have an equilibrium. You'll find your weak acid equations on page 13, so you can always check there as well. You should know your strong acids as you've been learning those since National 5. Thank you for watching this video. I hope you found it helpful. Please subscribe and follow me on Twitter at MissAdamsChem for updates on new videos.